Welcome to Tales from the Periodic Table. I'm your host, Ron Hipschman, and today we're going to talk about the element rhenium. As usual, I have a little sample of it for you in my vial right here. It may be a little hard to see. I put it on my scanner, though, so I can give you a magnified view of it. Actually, let's magnify that even a little more. You can see that it's a bright, shiny silver element. Here, we see the beautiful periodic table produced by Theodore Gray. As I've mentioned in previous episodes, Theo has written one of my favorite books called The Elements. I encourage you to pick that up. Check out his fantastic website, periodictable.com. Rhenium is the 75th element in the periodic table. Its atomic number is 75 because that's how many protons are in its nucleus, and that is what distinguishes it as a unique element. Dmitri Mendeleev tried to make sense of how the elements related to each other by arranging similar elements into columns. Here's his chart. He did a pretty good job for the time. You'll notice some familiar features. The alkali metals look like they do today. The alkaline earths look pretty good too, as long as you ignore the inclusion of zinc and cadmium. And the halogens aren't bad either, except for the possible inclusion of manganese. But below manganese, he had in particular a couple of blank spots for elements yet to be discovered. An early contender in the discovery of rhenium is the Japanese chemist Masataka Ogawa. He was working with an ore of the radioactive element thorium called thorionite. In 1909, he published he had discovered element 43, called technetium now. He named this element nipponium after his native country. Later chemists disputed this discovery, saying that what he actually observed was the element below element 43, rhenium. His two-letter symbol for nipponium, Np, was later reused for neptunium. However, in his honor, element 113, discovered in 2003 by a team of Japanese scientists, was named nihonium, also after the country of Japan. This whole story is still under some discussion. Credit for the discovery of rhenium is given to German chemists Otto Berg, Walter Nodak, and Ida Nodak. In 1925, they detected the element in the minerals columbite, gadolinite, and molybdenite, and in 1928, extracted 1 gram of the element after processing 660 kilograms of molybdenite. That's dedication. Indeed, molybdenite is the main commercial source of rhenium. Interestingly, rhenium was the last element discovered with a stable isotope. All subsequent discoveries were elements with only radioactive isotopes. More on isotopes in a few slides. From the Latin Rhenus, for the river Rhine, we get the name of this element, rhenium, an appropriate recognition of our 3 German discoverers. The world produces about 70 metric tons of rhenium annually. Most of the world's rhenium, about 40%, is mined in Chile. Poland and the U.S. supply about 13% each. Germany, 10%, and the remaining 22% by the other countries seen here. An additional 25 tons of rhenium per year comes from scrap and recycling. World production of rhenium has grown steadily in the past 50 years, from about 7 metric tons in 1973 to around 50 metric tons per year currently. Rhenium is pretty pricey stuff. Depending on purity and the quantity you buy, you'll be paying around $2,000 per kilogram. The top sample here is a zone-refined single crystal. The middle sample is an arc-melted piece, and the bottom is a machined 1 centimeter cube. You can find those cubes on the internet, and they go for $200 and up. They weigh about 21 grams. The price of rhenium, though expensive, remained essentially steady except for the sharp increase in prices after the 2007 credit crisis, where the price reached an astronomical $10,000 per kilogram. The price has since stabilized around $1,000 to $2,000 per kilogram. Just FYI, the current price of gold in 2023 is about $64,000 per kilogram, which is a bit odd, given that rhenium is rarer than gold in the crust of the Earth, as we'll see in a few slides. Rhenium is a part of a large group in the middle of the periodic table called the transition metals. This section of the periodic table is where we fill the d electron orbital of the respective atoms. Rhenium is a very beautiful grayish silvery metal. These are very pure arc-melted pellets. You can also buy these online, but be prepared to pay a pretty penny for them. A quick and crude estimation I just made seems to indicate that each of those blobs of rhenium will cost you about $600. The element rhenium is one of the rarest we've dealt with so far, coming in as the 80th most abundant element in the universe by mass at only 2 parts per 10 billion, right near the bottom of this chart. It's the 4th rarest element in the universe. Half as abundant in the Sun, it makes up only 1 part per 10 billion of its mass and is the 71st most abundant element there. Again, the 4th rarest element in the Sun. It's the 70th most abundant element in meteorites at 5 parts per 100 million. Even uncommon in the crust of the Earth, it's the 78th most common element at 4.6 parts per billion, a bit rarer than gold at 3.1 parts per billion. Rhenium is the 73rd most abundant element in the oceans, a very difficult to detect 1 part per 10 trillion. And lastly, like most of the elements in the upper reaches of the periodic table, there is no rhenium in us. This complicated version of the periodic table shows the evolution of the elements through the history of the universe. Here you see each element square with a tiny chart of its own, showing that element's growth over the age of the universe by various processes. Rhenium is here. I understand this looks complicated, but let's look at just rhenium a little closer. The horizontal axis of this square represents time, from the Big Bang to now. The vertical axis shows the proportion of rhenium created by various processes. About 1/8 of rhenium present today is believed to be produced by dying low-mass stars, the magenta area. Another 2/3 is produced in supernovae, the yellow area. A very small portion, that green icing on top, about 1/8, is produced in neutron star mergers. Each element has many different forms. For each specific element, the number of protons in the nucleus is the same, 75 protons for rhenium, but there can be different numbers of neutrons in the nucleus. All these different forms are called isotopes. They're chemically identical to each other, but with slightly different weights. The number you see next to the chemical symbol is the total number of protons and neutrons in the nucleus. There are 35 known isotopes of rhenium, and of these 35, there's only one stable, non-radioactive isotope, rhenium-185. Rhenium is therefore a monoisotopic element. There are 23 of those, by the way. You would think the only stable isotope would make up all of the naturally occurring rhenium in the universe, but it only makes up 37.4% of naturally occurring rhenium. What? As we'll see in the next slide, there's also a long-lived radioactive isotope, rhenium-187, that makes up the rest, coming in at 62.6%. There are only two other elements where the stable isotope is less common than its radioactive relatives. Those other two are indium and tellurium. By the way, the word isotope comes from the Greek isos, meaning same or equal, and topos, meaning place, since all these various forms of rhenium occupy the same place in the periodic table. Of the radioactive isotopes of rhenium, these are the longest lived, the ones with half-lives over 1 hour. More on half-life in the next slide. The longest rhenium half-life is rhenium-187 with a half-life over 41 billion years. That's almost 3 times the age of the universe, so we shouldn't be surprised to find a bit of this stuff still hanging around. What's a half-life? This graph shows an exponential decreasing curve. As an example, let's say we start with 1,024 atoms of any isotope from the previous slide. I chose 1,024 atoms because it's a power of 2, and we'll be doing a lot of divisions by 2. If you wait 1 half-life, half of your isotope will decay, and you'll have 512 atoms left. If you wait 1 more half-life, half of that half decays, leaving you with 1/4 of the original 1,024, or 256 atoms. Another half-life, half again as many, or 128 atoms, and so on. Just keep dividing by 2 every half-life. After 10 half-lives, you'll have about 1/1000th of your original amount. By the way, notice there's 1 remaining atom after 10 half-lives? If you waited 1 more half-life, your remaining atom would have a 50-50 chance of decaying in that time. Rhenium has a very high density at 21.02 grams per cubic centimeter. As a reminder, water has a density of 1 gram per cubic centimeter. I've put up more densities for you here. You can see that rhenium is even denser than tungsten or gold, and those are pretty dense elements near the top of the list. Here's a graph of the elements from highest density to lowest density. I have a set of blocks so you can feel density for yourself in my live talks. My set of blocks have a wide range of densities, with the densest at tungsten, to lead, to copper, to iron, to titanium, to aluminum, to magnesium. I also have plastic and wood blocks, but those are not technically elements. Again, rhenium's density is 21.02 grams per cubic centimeter, the magenta circle. It's the 4th densest element. I'd love to have a cube of this stuff, but at its current cost, that cube would be almost $8,000. Any rhenium refiners out there, I'm open to the donation of a 2¼ inch cube if you're so inclined to add to my collection. Being one of the refractory metals I'll discuss in a bit, rhenium has the extremely high melting point of 3,186 degrees Celsius, or 5,767 degrees Fahrenheit. It has the 3rd highest melting point of the elements. Rhenium boils at a blistering 5,596 degrees Celsius. That's 10,105 degrees Fahrenheit, giving it the highest boiling point of all the elements. That's a whopping 2,410 degrees Celsius above its melting point. Rhenium has the 11th largest liquid temperature range of all the elements. The high melting point makes rhenium a member of a class of metals called refractory metals. These metals are extraordinarily resistant to heat and wear. They all share some properties, including a melting point above 2,000 degrees Celsius and high hardness at room temperature. They're chemically inert and have high densities. Though not quite as tough as the classic refractory metals we just discussed, some of the other transition metals surrounding our central group share some of the same qualities, but to a somewhat lesser extent. Note that technetium is not included in this group since it must be made artificially and is highly radioactive. If we compare the size of the rhenium atom to that of hydrogen, we'd see something like this. The rhenium atom is about 3.5 times the size of hydrogen. Here's its electron structure. By the way, a picometer is a trillionth of a meter. Atoms are impressively small. Looking at all the element atom sizes, here we see them sorted from largest, cesium at the top left, to smallest, helium at the bottom right. Rhenium has the 28th largest atom of the elements. Rhenium is hard stuff, coming in at 7 on Mohs scale of hardness, about the same as quartz. A compound of rhenium, rhenium diboride, is even harder at 9.5 to 10, very close to diamond. In one crystal orientation, you can even scratch diamond with rhenium diboride, meaning it's even harder than diamond. Here's a chart of element hardness from the hardest, boron on the left, to the softest, cesium on the right. Obviously not including liquids or gases. Rhenium is the 5th hardest element, between osmium and vanadium. Rhenium has the 10th lowest rate of thermal expansion of all the elements, only 6.2 parts per million per Celsius degree. This means that if you had a 1 meter long bar of rhenium and you heated it by 1 degree Celsius, it would get longer by only 6.2 millionths of a meter, about 1/10 the diameter of a human hair. A pretty low expansion rate. Here's the periodic table of the spectra. Rhenium has a moderately complex set of emission lines across the spectrum. If I increase the contrast, you can see this more plainly. These emission colors uniquely identify it as rhenium to scientists. No other element gives off this set of colors. Let's take a look at a few applications of rhenium. Many of these are for its high melting refractory nature. Some applications are for its incredible density, but there are electronic and medical applications as well. Rhenium is a critical component in superalloys used in the aerospace industry. These superalloys are employed where temperatures can reach well above 1,000 degrees Celsius or 1,832 degrees Fahrenheit. Rhenium enhances the strength and stability of these alloys, allowing for higher engine efficiency and longer service life. These alloys are commonly used in aircraft engines and even in space exploration, such as rocket engines. Rhenium can make up to 6% of these superalloys. This accounts for almost 77% of rhenium usage. Here is an extremely expensive, pure rhenium rocket exhaust nozzle. To give some perspective, this is about 3 inches across, so is probably for a correction thruster. The second most important use of rhenium is in combination with platinum as catalysts in the production of gasoline. Platinum-rhenium catalysts help turn low-octane precursors into high-octane additives that are blended into our fuel. Hopefully, this use of rhenium will be reduced as we move past CO2-producing internal combustion engines. A more ecological place, rhenium catalysts may be found in the harsh environment of fuel cells. Toyota has used hydrogen fuel cells in a car you can actually buy, the Mirai. The fuel cell in this car turns its fuel, hydrogen gas, and oxygen from the atmosphere into electric power. The only thing that comes out of this tailpipe is water vapor. Most X-rays are made by smashing high-speed electrons into a dense metal target. Electrons are produced by a hot filament. The electrons are accelerated by a high voltage towards a metal target. This target is often made of tungsten, but sometimes rhenium is employed. Stopping the electrons creates X-rays. This is called Bremsstrahlung, from the German for breaking radiation. For high-intensity beams, the target can get extremely hot, so you need a dense metal target with a high melting point. One way to keep the target from heating up is to spin it under the stream of electrons, exposing a larger area and spreading the heat around. That's what you see here. The lower metal disc is spun during the X-ray production. This tube is not energized, so is not producing any X-rays. Rhenium alloys, such as tungsten rhenium and molybdenum rhenium, are used to create thermocouples. Thermocouples turn a temperature difference into a voltage, so you can measure the temperature. Since they're made from refractory metals, these temperature sensors can operate in extreme conditions, in high-temperature industrial processes, scientific research, and space exploration. This is a rhenium sputtering target. It's used in a sputter coating apparatus like this one to coat a specimen with a thin layer of metal. Air is drawn out of the glass chamber with a vacuum pump and replaced with an inert gas such as argon at a low pressure. A high voltage is applied across the chamber, creating a plasma between the rhenium target, mounted near the top of the glass vacuum chamber, and a specimen you'd like to coat, mounted below. The plasma knocks atoms off the target, which are deposited on the specimen. If you want to view a specimen in an electron microscope, it usually must be electrically conductive. The sputter coater coats it with a metal, such as gold, palladium, or rhenium. Here you see a gold sputter-coated ant ready for the electron microscope. While rhenium would make great lamp filaments, just like tungsten, it's a bit pricey. Still, it does find some uses, like this filament for a mass spectrometer. Here, the filament vaporizes the substance, which then passes into the mass spec for analysis. Here is a small tungsten rhenium filament. This glowing filament is the source of electrons used in an electron microscope to bombard the specimen. The phenomenon of electrons emitted from a hot filament is called thermionic emission. Rhenium has low contact resistance and excellent electrical conductivity, which makes it ideal for use in electrical contacts, especially in high-temperature environments. It's used in switches and connectors for aerospace and defense applications. Rhenium is used in nuclear medicine. Stable rhenium-185 is bombarded with neutrons, converting it to radioactive rhenium-186. Rhenium-186 decays by emitting a beta particle, an electron, that can destroy tumor cells. It also emits a gamma-ray photon used to image the tumor from outside the body. 2 emissions for the price of 1 atom. You get both treatment and diagnostic information. The emission of the beta particle transmutes the rhenium-186 into stable osmium-187. Here's a bone scan of a patient with a metastatic tumor on his ribs, and 6 months after rhenium-186 treatment, the tumor has disappeared. Now, you don't just inject a patient with radioactive rhenium metal. The radioactive rhenium is part of a much more complicated molecule that will target the specific type of cancer being treated. As detailed earlier, highly abundant radioactive rhenium-187 has a long 41 billion year half-life, which is long enough to make it useful for dating rocks and minerals. Rhenium-187 decays to stable osmium-187, and by comparing the 2 isotopes, one can determine how long the containing mineral has been around. This works for minerals where you might find rhenium, such as gold, copper, and nickel ores. Please note I've grossly oversimplified this process, but you get the basic idea. Aside from a tiny bit possibly absorbed from the environment, your body does not use rhenium, and it has no known biological functions. It appears that rhenium is not very toxic, though only a few studies have been carried out. Going off on a tangent for the moment, the album Rhenium was released in 1996 by the ultimate funk group Parliament with the amazing George Clinton. Oddly enough, this album was really a re-release of Parliament's very first album, Osmium, which happens to be the next element in this series. I'm comforted by the fact that George Clinton is as obsessed with the periodic table as I am. As usual, we'll end this talk with Mary Soon Lee's elemental haiku about rhenium. 1925. Found. New element. Stable. The last to be caught. As I've already mentioned, the next program in this series, I'll examine another high-melting refractory element, osmium. I hope you'll join me. I'm your host, Ron Hipschman. Thank you for watching this Tales from the Periodic Table program about the element rhenium.